All right. Hello, everybody at home. This is Miss Sinclair. It is Tuesday, March 23rd. We're doing lesson 22 today. So I want to point out something at the top of lesson 22. Get your highlighters ready. It says, predict how many times you can fold a piece of paper in half. And then right here is where you're going to put your prediction. So before we start folding our paper in half, I want you to look at a regular sheet of just any old kind of paper. And if you're home, get any old kind of notebook paper. And try and guess how many times you think you can fold this in half. And put the guess right here. And then don't start folding yet until we have a conversation about that. So if I don't fold this at all, how many layers of paper is this? Ethan? One. So on your worksheet, if I don't fold it at all, I have one layer of paper. Let's fold it one time in half. So you're going to take your paper, you're going to fold it in half one time. And there you go. Okay, now how many layers of paper do I have? Ethan? So you have 2 layers of paper right there. Let's fold it in half one more time. So it's going to look like this. Now how many layers of paper do I have? Ethan? All right. I'm going to challenge you to see how many times you can fold that paper in half. But each time you fold it, you have to answer how many layers of paper are in your packet. Go. I'll give you about 3 minutes to see how far you can get. Tyler. Aiden, folding your paper. Good job. And what we're going to be looking for is a pattern in this table. Fold it in half one more time. You looking for the pattern? Okay. It's hard to do at the end, isn't it? So somebody raise your hand and tell me, how many times were you able to fold your paper? Derek? 6 times. Caleb?
I got 5 layers and 15.
Okay. So how about you, Brooklyn? How many times did you get to fold yours?
A lot.
You didn't count?
No.
Okay. I can tell you almost everybody got 6.
I can get one more.
There are a couple of people that got to 7. So let me show you the numbers that go in your table, okay? Here are the numbers that you're going to fill in. If you folded it 3 times, there's 8 layers of paper. 4 times, there's 16 layers of paper. 5 times, there's 32 layers of paper. Anybody see a pattern in these numbers yet? Brooklyn? Not counting by twos, but you're really close.
You're at
Starts with a D.
What?
Starts with a D. What am I doing? Dominic? No, I'm doubling every time. So you're right, it was 2 times. So watch this. Double of this, double that, double that, double that. See how it works? This is 128. This is 256. Go ahead and fill in the rest of the numbers on your table for the layers of paper. Then put that down. And then we're going to look for another pattern. So look at these 2. Let's look right here. Ethan, we're ready to move on. We talked about once upon a time, when we first did exponents, we said any number to the power of 0 would always be 1. You guys remember that? Way back in the day? Any number to the power of 1 was itself. If I follow this pattern, what's going to happen? Go ahead and finish the pattern. Now look at these two tables. Look at these two columns. Tell me if you see it. Oh, I got 5 hands up right away. Everybody look. Can you see it? Look down these rows. What do you see, Tyler? Huh? Nope. Comparing these two columns. Don't just look at this one or this one. Compare these two to each other. Jackson, what do you see?
For the numbers of fold is the number behind 2.
Exactly. The number of folds is the exponent. 1 fold to the first power, 2 folds to the second power, 3 folds to the fourth power. You know what this is called? This is called exponential growth. When something doubles or triples every single time it goes through an iteration, it's growing by an exponent of 2. Here's my next question. Get your highlighters ready. Were you able to continue folding that paper indefinitely? Yes or no? Could you keep on folding and folding and folding and folding and folding and never stop? No. Why not? What happened? Ethan?
It gets rougher every time.
It gets rougher every time. Ashlyn?
It gets harder because the paper's coming off.
Yep. Parker?
The paper's getting too thick for us.
Especially at the corners when you had to fold it over, it gets too thick, right? Well, let me ask you a different question then. Turn the page. Let's go look at question 3 and consider this. If we weren't folding the paper, what if we just cut it in half each time and then stacked the stack up on top? Would we be able to go on? If we were cutting it, could we stack it up? Yes, we could. Yes, we could stack that right up. Then it says, how many layers of paper for 16 cuts? Now remember, when we said on this page, the number of folds was the exponent. Oops. The number of folds was the exponent, right? So that'll be the number of cuts, would still be the exponent. So let's look. If I cut it 16 times, it's going to be 2, and what's my exponent going to be? 16. It's 2 to the 16th power. Now, if you wrote 2 to the 16th power, Thomas, it's going to be a number like way, 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 way long. We're going to find out in a minute that if you go through to the 20th power, you're past 1 million. So you don't want to have to write giganto numbers. So you use an exponent notation to show a great big value and not take up half a page to write the number. Does that make sense? This is like code for making it short. Okay, here's what we're going to do next. We're going to talk about a science problem. You should talk to Miss Smidra about this. It's kind of a cool story. It says bacteria are microscopic single-cell organisms that reproduce in a couple of different ways. One of the ways is called binary fission. I'm going to write that up here. Binary fission. Write that word. This is how this bacteria reproduces. Caden, did you write that down for me? When you don't know what the word binary means, you got to look at the parts of the word. And I'm going to say, look at this part of this word. Does anybody know what it means when they use the word bi? As in binary. Peyton? Huh? Bold? Both. Binary means 2. Here's the thing. Bicycle has how many tires? 2. So binary is 2. So what this bacteria does, this is what's so cool about this story. Ready? It says, a bacterium increases its size until it's large enough to split into 2 parts that are identical. Then those 2 parts grow until they're large enough to split into two. So look what happens on the picture. Put it down, please. No, just leave it there, Tyler. It's bothering you. It's bothering me. Just leave it. So we start with one. It splits in two. And each of these splits in two. Splits in two. Each of these splits in two. See what keeps happening? So let's take a look over here. Here's a data representation of binary fission. First generation, that one organism creates two more. In the next generation, it doubles. In the next generation, it doubles. In the next generation, it doubles. Every time I get here, I'm going to take that number, multiply by 2, and it's going to keep growing. And that's as far as I can go in my head. So write those down. And then we're going to pull out the calculator. You ready? After only 10 generations, we went from 2 to over 1,000. Let's keep doubling those numbers. You can see how big the numbers start to get, right? We know from the first time we did this that the number of generations is going to be the exponent. So now we can finish this pattern over here. That's a lot. So see how you can take a large number like 16,384, write it in shorthand kind of thing. Yes? Question? Okay. This is why I think this is kind of a cool thing to talk about, because look at this question it says. How many generations would it take until there were over 1 million? Now, after 14 generations, I'm already at 16,000. So I'm going to write a 14 over here because I know I've already done 14 generations. Here's what I'm going to do next. And Brooklyn, would you be willing to make like tally marks for me on your paper? A tally mark for each time? Watch this. So every time I times that by 2, just make 1 mark on your paper. Okay, you ready? Let's see how long it takes us to get to 1 million. 1 tally mark, right? I passed 1 million now. How many times?
6.
So watch this. If I started with 14, it took me 6 more. In 20 generations, I passed 1 million. Right. So in 20 generations, so think about this. Now we know why the coronavirus spread the way it did. It spread just like that. It spread exponentially. So if you walk down the street and somebody next to you has COVID and they pass 5 people, all 5 of those people could get it, and then they're going to walk past somebody and they're going to give it. So exponentially, that's how those things happen. That's why it took over, everywhere. All right, now here's the next cool thing. Watch this. Under the right growing conditions, bacteria can reproduce every 15 minutes. So I can get 1 generation in 15 minutes? Thomas, put that down, please, because I'm looking for numbers on your paper. So if I can do one generation in 15 minutes, who can tell me how many minutes are in an hour? Peyton? So 60 minutes. So this is the top number is the generations and the denominator is the minutes. Watch this. This is what's so cool. How do I switch from 15 up to 60? How many 15s minutes are in an hour? Derek? So watch this, 4/4. Remember when we switched fractions around? So that says I can get 4 generations in 1 hour. 60 minutes is an hour, right? So let's watch it this way. How many generations per hour can I get? I can get 4 generations in 1 hour. We're not that far yet. You ready? We just figured out it took 20 generations to pass 1 million, right? So generations is my top number. In 20 generations, how many hours will it take? How do I go from 4 up to 20? Peyton? 4 times 5 is 20. 1 times 5 is 5. I get 1 million bacteria in 5 hours. 1 million in 5 hours. That's why COVID happened the way that it did. That is called exponential growth. We're not just adding 5 every time. We're doubling every time. That's a whole different story about math. Okay, we're on the problem set. Well, no, we're not. Let's see.
Yeah, we are. Go, one more page.
No, let me think about this. We're going to skip that page. We're going to go to problem set. Question 1. You guys ready? Question 1. A checkerboard has 64 squares. So you'll notice the squares are numbered all the way down to 64, right? We know that 20 generations, which is what we just did, is over 1 million. So by the time I get to this box, the 20th generation, I got to fit a number in there that's 1 million and something. So what does that tell you about how this is going to work in this table? Caleb?
We're going to have to write really small so we're going to fit big numbers.
Yeah, not even possible to fit them in there. So what are we going to use instead of the whole number? Ethan? We're going to use the exponent. Exactly right. Okay? So you ready? 1 grain of rice on 1 square. Second checkerboard is going to be 2. Oh, wait. How do I write this? Let me think about it. This is going to be 2 to the first power, which means this over here has to be 2 to the 0 power, because we're doubling every time. So remember, anything to the 0 power equals 1. Anything to the first power equals itself. And this is going to be what? 2 to the second and 2 to the third. And by the time we get to the very end, way down here, it's going to be 2 to the 64th power. Now, are we going to spend all this time filling this in? No. The purpose of showing you this is that you understand that writing, if we're already at 1 million here, where do you think we're going to end up by the time we do it 44 more times? Beyond a number we could ever put on paper, right? Really?
I just looked in it. So by the time we reach 64, we're going to be at 3 million something.
Oh, way past 3 million, because, watch this, Caleb, show me this. If we're at over 1 million here, and I double that, this is going to be more than 2 million.
Yeah, I was thinking.
and then 4 million, and then 8 million, and then, you know what I'm saying? So the numbers are going to be so big, they're not manageable. And that's why math came up with this like shorthand way to talk about really, 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 really big numbers. Make sense? Let's look at the last page. We're going to do one more thing together today. Okay, back in the olden days, when I was a principal in South Haven, let me finish. Back in the olden days, in the 2000s, so 21 years ago, I was a principal in South Haven. And what happened when you had a snow day back in the olden days was you had to use the phone. You didn't get text alerts. You didn't get it any other way. And actually, they would call the TV stations and they would tell Channel 3 to put it on the news, right? But I had to make sure the teachers that worked for me knew early enough so they didn't get ready and go to work. So this is what used to happen back in the day. The athletic director at a school has created a phone tree. So we had what was called a phone tree. I'm going to show you what that looks like. Back in the olden days, we used that to notify people in the event that something had to get canceled. A phone tree is initiated when the director calls two captains. So we'll just change it to principal and teachers, okay? So here I am, I'm the principal. The bus garage calls me. So the bus garage drives around out at like 4 o'clock in the morning, and they take a bus out and they try and drive the bus on those back roads to see if they can stay on the road or if they're going to go in a ditch. So after they take a bus out, they decide are we going to have school or not, and then they start making phone calls. So the superintendent calls the principal. And then the principal has to call two teachers. And then what do you think happens next? Kaden? Nope. Nope. Ashlyn? Nope. How many teachers have I called? How many people know now? 2 teachers. I got 25 teachers.
Oh, teacher called the other teacher.
So this teacher calls 2 people. And this teacher calls 2 people. Because y'all have to just wait to find it on the news. Miss Malone will remember this. Phone trees back in the day when we had snow days. Then this teacher calls how many people?
2.
Well, let's finish it and see. Now, I hope you can read your own writing. So, listen, if the superintendent calls the principal and the principal calls 2 teachers and then they all start calling, let's count and see how many teachers have gotten a phone call. At this first stage, only 2 teachers got a phone call, right? At the next level, how many more? 4 more. So these 2 plus 4 more equals 1, 2, 3, 4, 5, 6 teachers now know, right? And each of these teachers call 2 more people. So 6, 7, 8, 9, 10, 11, 12, 13. Now we're up to 14 teachers. I had 25 teachers in my school. Did everybody get a phone call yet?
No.
Okay, we have to make another round of phone calls.
It's 2. I think that is 164.
That's 16 more. So now I'm at 30. So I've got everybody covered now, right? Now, Miss Malone can tell you the worst possible thing that could happen is this person right here doesn't answer their phone. What do you think's going to happen? All of these people don't get a phone call. And then what happens? No. They all get ready to go to work. You know how mad they are at that person? Oh, isn't that happening?
Seems like a fun time. Well,
Not a fun time. Yes.
what if the other teachers call them that already know that there's no student?
How did they know that the other person didn't get a call?
They
You wouldn't know that, right?
They didn't put the phone, so they informed others.
I don't know. It's happened. I'm just saying. Then then what I did, because I got this phone call at about 5 a.m. It took me a while to get all my numbers and call people. So by 5:30 a.m., I'm now wide awake because I had to call people. So you know what I did? I went and I woke up my kids to tell them there was no school and they didn't have to wake up.
Oh my!
I hate my parents do that.
They did not appreciate that.
I love when my parents do that.
They did not think that was funny.
My dad did that to me. And then get in the car and go to the school and then realize that nothing happened.
We're going to go back and do one more problem and then we're going to take a break. You guys ready? Please find example 3. Go back a couple of pages.
Wow.
This is another example. Another example. I like the other 2 examples better. That's why I did those first. We talked about why COVID spread so fast. Because each generation, it kept growing by exponential numbers. And then we talked about phone trees. But now we're going to talk about this. So we did this a while ago. We talked about volume of a 3-dimensional picture. And we said to find the volume, you go length times width times height. Do you guys remember that? Yes, no? Yes, you should. You ready? You ready? Thomas, I've asked you to put that paper folding thing down. I just need you to get your regular work done. So when we multiply 3 different dimensions, is my answer going to be 2D or 3D?
3D.
Is that a 2D or a 3D picture? 3D, right? So right here it says the width is just W. Then it says the length is 3W. So I'm going to go over here and put that. And the height is 2W. And when I multiply them all together, what happens? 3 times 1 times 2. Just do the numbers. Multiply the numbers first. Dominic, 3 times 1 times 2 is 6. And what if I multiply W times W times W? What do I get? What do I get? Multiply W times itself 3 times. Caleb?
W to the third power.
Yes. Like this. It's not 3W. It's W times W times W. Does that make sense?
6W to the third power.
6W to the third power.
Very interesting.
Okay, let's look at this. Let's take 3W times W times 2W, and let me challenge you to double that. So what is double of 3? What's double of W?
W to the second power.
Nope.
2W.
Yep. And what if I double 2W? I get 4W. That's going to be a bigger box, isn't it? Now when I multiply, what would I get? 6 times 2 times 4. Well, I would, because you can rearrange them any way you want, right? So do 2 times 4 first.